In this segment, we're going to discuss a new feature in Builder 2020 that allows users to modify and override the modulus of rupture of concrete. This new feature is found in Criteria under the Concrete tab, and we can see for any given concrete that's defined, we can either use the default value being 7.5 times the square root of the defined compressive strength of the concrete, F'(C), or the user can simply select FR and directly enter that value here in PSI or MPa for SI units. You can see in this example we have 4 concretes defined. We have 7.5 squared F'(C). All of the F'(C) values are set to 5,000. We have 6, 5, and 4 times square root of F'(C), and those are defined again in terms of PSI. In the example that we're running here, we have 2 stacks of post-tensioned slabs. These are two-way slabs, and then RC slabs on the right side. If I turn the post-tensioning on, we can see that post-tensioning here. And also to note, under the Criteria Analysis and Design Options tab, there's also, under Design Code rather, there's now the option for ACI 2019. When this is selected, the program will use the new methodology for I effective per Bischoff's method. If we use 2014, it then reverts to the previous methodology for calculation of I effective. Now the rupture modulus comes into play when we check cracking for a slab in Adapt Builder. So if we go to loading and load combinations, we can see here we have 2 combinations. Really, one is crack deflection, so this is the combination that will actually use that value for rupture modulus when it calculates the cracking moment and then reduces the gross moment of inertia down to I effective. And then we have long term, which essentially just references this crack deflection combination called total load. So the steps by which we go ahead and run this, and the workflow really, is first to mesh the models. So we'll go ahead and we'll mesh these. We'll mesh using the default values, 3 feet and a 1.5 foot node shift value. We're then going to execute the analysis. We're going to run the analysis for all of the combinations. Before we take this a step further to design the sections, which is required and a prerequisite for running the crack deflection, we can go ahead and pause here, and for the just the regular service combinations, total, for example, or service sustained, if I look at the deflections for the slab and those contours, we can see that the deflections will be identical. So regardless of the input for the modulus of rupture, that's not being used here. This is purely a function of just the stiffness and properties of the concrete in terms of what's been modeled. All of these are identical for the post-tension slabs, and then they're all identical also for the RC slabs. So taking this a step further now, we're going to select floor design. I'm going to generate the design cuts, and then I'll design those cuts. We need to have an accounting of all the reinforcement in the slab before we run the crack deflection check. We'll go ahead and select yes to save the design of those sections, and then finally the third step here after meshing is to run the crack deflection. So this will rerun the analysis using the effective moments of inertia for each of the design cuts. If we go back to the deflection for the crack deflection combination, we'll go to loads under the result display settings or the results browser. For crack deflection, we're going to select cracked total load. We could also use long-term or cracked long-term and produce the deflection contours, but we'll just use the cracked total load here. And if I go to the Z direction again, you're going to see the deflection increase as we move from top to bottom due to the change in the modulus of rupture for each of the different slabs. And we should see that the slab on the lower right, this is the reinforced concrete slab, has max deflection, but we could also compare the values and the contours for each of these slabs. Again, this slab here, if we mark these, this slab is 7.5 square root of F'(C), and we work our way all the way down to 4 square root of F'(C). The same type of an approach can be used for a one-way slab with beams. In this example, we have beams in the model. Let's go ahead and turn those beams on. In view, we can see we have beams in the Y direction and then the one-way slab spanning in the X direction. And again, in the stack of columns on the left side, we have post-tensioning. So we have post-tension beams with one-way slabs, and then we have RC beams and one-way slabs on the other side. The only real difference here, aside from just assigning the modulus of ruptures in any really user-defined way possible, is that the beams here will actually show loss of stiffness also, which is a good indicator of or prediction of the change in the modulus of rupture, indirect kind of predictor of that. So in this case, we'll run the same process. We're going to analyze design sections, run crack deflection, and then we can show those deflection results either again in contour form. We can also show them on beams separate of contours, and then we can also show the loss of stiffness values as well. And we'll do all three in this run. In this model, we do use the same identical load combinations and load cases. So everything really is identical other than the actual structural configuration and what's modeled. Again, we're going to generate the design cuts. Now in this case, instead of having two-way slabs, these are now defined as beams in the Y direction, and in the X direction we have one-way slabs. And here we see those one-way slab strips, and if we double click again we can see that they're set to a one-way slab, and that's for all of the different strips. We do have some strips leaking out here of the slab regions, so to avoid that, what I'm going to do is just delete out these support lines here, and that shouldn't affect the results too much in this case. So we have our one-way slab strips. We're going to now design all of the slabs and the beams in order to again get an accounting of all the reinforcement per the design. We'll save that design, and then finally we're going to run the crack deflection again, and we'll get a new result here for the model with beams and one-way slabs. Okay, we'll go ahead and select OK to save the crack deflection results, and again we can access those results from the result browser here on the right hand side of the screen. The result shown is similar to that of the two-way slab, where we have increasing deflections as we move top to bottom, or as we move from a higher cracking modulus or modulus of rupture down to a lower modulus of rupture for both the PT and also the RC system. And again, we're selecting the cracked total load combination. If we switch this over to long-term, we should see similar results, just with a multiplier on top of this to predict the long-term cracked deflection. So this might bump up to several inches, probably 6.12 inches as shown here. And again, increasing from top to bottom, or from a higher FR value down to a lower FR value. We're going to go ahead now and just turn off the contour result. I'll come back to the cracked deflection combination, cracked total load, and we can also show the reduced I effective value for beams or for slabs. I'm going to show it for beams here. We're going to go here to actions. I'm going to use the reduced stiffness ratio value like so. If I zoom in, we can see, for example, that the beams with the higher modulus of rupture at the center of the span, where we have the most bending and deformation, we can see that the modulus of rupture here is about, or the I effective over I gross ratio is 0.33. As we lower the modulus of rupture, that value should increase. We get down to 0.28. This here is with 5 square root of F prime C, that's 0.26. And then finally, we have 0.24. On the RC side, we have something similar. We have, 0.31, 0.2, 0.19. So this is lower. Obviously, we don't have the counteractive nature of the post-tensioning cables in those beams, so we have more stress on the bottom fiber and midspan, to 0.17, and then we get 0.16, and then the lower value here is 0.16. Now these two might be the same simply because we're having to add so much reinforcement in this system with the lower modulus that ultimately we get some limitation on the bottom end value of I effective in these two models. But this is how we can show that value for loss of stiffness for beams, and then we can also show that for slabs as well. So if I go back to the slab option under slab actions, you can see the reduced rotational stiffness about the x-axis. This is for the slabs, or let's say the flange of the slab, for this cracked total condition. You can see again loss of stiffness contours with different varying levels of modulus of rupture.